Welcome to Physics Made Easy channel, and now I will proceed from the previous concept. And here we have got a shortcut. We have just discussed one shortcut and a screen. Now the next basic concept, basics. A screen is placed 50 centimeter from the slit, which is illuminated by 6,000 angstroms light. If the distance between the first and the third minima in diffraction pattern is given, distance between the first and the third minima, x3 minus x1. Very simple. This is the condition for minima. The condition for minima is, now I will write a general formula. This is x delta x. Distance is given. Now this is x n plus m minus xn. So this will be equal to lambda capital D by A into, we have got n plus m minus n. This cancels. So it means, now note down this shortcut. In such problem, lambda D by A, here I shall be having just m. M is the difference between the minima. M is equal to 2 in this case. So actually he has solved this problem using this formula. I can even write this as delta M. Delta M is the difference between the order of the two minimas. In this case, it was first order and third order. Had it been me first order and fifth order means 5 minus 1. 5 minus 1 means 4. Delta M is equal to 4. Had it been me sixth order and first order, then 6 minus 1. Delta M is equal to 5. In this way, you can make use of this shortcut. This shortcut was when it is the same secondary maxima or minima, but two wavelengths are used, and here same wavelength is used, but we are given the distance between two minimas or two maximas. Then you can make use of this formula. So this is a particular case of maximas. No, it is minimas. Next problem. In a single slit diffraction experiment, first minimum of red light coincides with the first maximum of some other wavelength. Now quite clear. First minimum for red light. This you can say sine theta is n lambda red by A. And the same sine theta is equal to first minimum. First minima means n is equal to 1. Take n is equal to 1. Say first minima sum coincides with the first maxima. Now the first maxima, this is the condition for first minima. The condition for first maxima is this. Now these two coincides. These two are the same. From here you can find out lambda. Quite easy. First minima is lambda for red color. First minima is lambda R by A. And first maxima for another wavelength is 3 by 2 lambda divided by A. One third of this, in this, no, sorry, 2/3 of this you can find out. This is 440. Again, remember the first minima of red light. First minima of red light is given by lambda R, lambda red I mean to say, lambda red by A. And the first maxima for some other wavelength, he is taking it as lambda dash. I will also take it as lambda dash. So first for in see in this equation for first maxima n will be equal to 1. If n is 1, then this will become 3. 3 by 2 into lambda dash by a. So nothing new, very easy problems, and we have picked up only those problems which are relevant and upon which questions have been asked in recent future and not in the remote future. And let me go to the next problem. What should be the width of each slit to obtain 10 maximas of double slit interface? This question has been asked many times. What should be the width of each slit to obtain 10 maximas of double slit pattern within the central maxima of single slit diffraction? Now, this is the single slit diffraction. 2 theta. In 2 theta width of central maxima is 2 lambda by a. Now in 2 theta, condition for maxima in nth maxima, condition for nth maxima is in I mean to say diffraction in interference, condition for nth maxima is n lambda by d, where d is the distance between the two sources. Now for 10, n will be this. How do we calculate it? In that case, we have got a formula like this. This is the condition for maxima in case of interference. Now xn by d, this xn by d gives us angular width, capital D. So this x by capital D gives us angular width. This becomes 2 theta, and 2 theta is n lambda by a. Now for 10, this n will be equal to 10. This is the condition of maxima. I am discussing it for interference. Listen again. X is equal to n lambda d by small d. X by capital D. Capital D is the distance of screen. X by capital D gives us angular width. So I can also draw a symbolic diagram for this. So in a very small space here, so that you can understand. So this is one screen, and this is diagram will be approximate one. So this is, I'm taking this as a screen, and here are the two sources. This is the central point. It is illuminating the two sources like this, and here these are the straight lines that go straight, and from here I am having one value like this, and from here we are taking it like this. So these two are the sources. These two are the sources. Now from here, this line, this angle is theta. This angle is theta. And this theta is, now let me take it from here, that will make things more clear. Let me take it from the central point, and let me remove this line. I will take it from the central point. Actually I wanted to have, no. So from here, this angle is theta. So say this is the central line, This is exactly the center line, and this angle is theta. This angle is theta. This angle is theta. In interference, I am drawing again the diagram is rough one. So obviously you will excuse. Now this is theta. Now this distance is x, and this distance from the source to the screen is d. Now it is clear this is theta. Theta is x by d. I will even remove this line. That will make diagram more clear. Yes, that will make diagram more clear. Now, this is theta. This is theta. I am taking it from the central point between the two slits. This theta and this distance is x. X is the distance of, you can say, this is the angular separation of 10th maxima. This is x. So 10 maxima have been included here according to this diagram. This x by d. D is the, it is capital D. This x by d is theta. And now once we divide this x by this d, I will get theta. I am taking it 2 theta because here I have taken the angular separation to be 2 theta. And now I will make these two equations equal. One is 2 lambda by a. This is width of diffraction pattern. Width of diffraction pattern is this. Now how will it look? Now if I assume the same diagram, so this is the width of the central maxima up to this point, and here we shall be having 10 maximas, 5 on this side. It's very tough to drive 5. I have just 3, 4, 5 maximas of interference pattern on this side, and 4, I would like to say 4. This is third, and this is 4. 4 on this side, 4 on this side, 4 on no. It's 5 on both sides. So it should be 10 maximas here. So these maximas in interference pattern should be 10. This is what this problem says. So this is the width of the central maxima for diffraction pattern. 10 maximas of interference pattern should be there. So this I have visualized you the problem. And now coming to this point here. Now these two should be equal. D is the distance between two sources. A is the width of aperture which has been used for diffraction. From here this is 5. Lambda cancels with lambda, and I calculated the value of D to be 5A, or A to be equal to D by 5. So this is an important problem, has been asked twice or thrice in different kind of examinations. And now let us see the next concept. A slit of width D, let me change the color. A slit of width D is illuminated by white light. For what value of D? The first minimum for red light located at a point P at 30 degree. For what value of the wavelength of the light will the first diffraction maxima also fall at P? Now, a slit of width D is illuminated by white light. For what value of D is the first minimum for red light? First minimum for red light. This will be D sine theta is equal to lambda. Located at 30 degree. Located at 30 degree, sine 30, this is D by 2 is equal to lambda. It's quite easy. From here we can make the calculations, and let me put the things in center, because here d sine theta is equal to lambda, and this theta is 30, sine theta is equal to sine 30 is 1 by 2, this is d by 2 is equal to lambda, and this wavelength is given 650 nanometers. For what value of the wavelength of light will the first diffraction maxima fall at P? Now diffraction maxima should fall at P, and we have to find out the wavelength. So for diffraction maxima to fall at P, first diffraction maxima, the condition for first diffraction maxima is d sine theta is equal to 2n plus 1 into, say, lambda by this 2. Now this is 30 is given, d is given, you can find out lambda, nothing new. Two wavelengths of sodium light, this and this, are used in turn to study diffraction taking place at single slit. The distance between the screen is 1.5 centimeter. Calculate the separation between the position of first maxima. We have done it already. We have done this problem already, a similar problem of this nature. So this is the shortcut for this problem. I have also devised another shortcut. You can see my previous lecture. Now this is a resolving power of microscope and telescope. We will discuss this in my next lecture. And up to this lecture, before finishing this lecture, I will request all of you to view these videos, and if you find something good in these videos, then kindly share. If not, then kindly comment so that we can improve ourselves. And thank you for being with me for 17 minutes.